Welcome, my name is Kim Hosen. I'm the Executive Director of Prince William Conservation Alliance, and we are just delighted that so many people could join us today. We're able to offer this program and others free of charge, thanks to community contributions. So we hope you will join us and check out opportunities on our webpage. Right now, we have a rain barrel raffle, which is a 60-gallon rain barrel hand-painted by award-winning artist James Gallagher. For every $20 you contribute, you get 5 chances to win this fabulous rain barrel and brighten up your personal landscape. Our topic today is stormwater, which is something that affects us all. And managing it is easier said than done. We are lucky to have Jake Hosen with us today, who is also my son. He is an assistant professor at the Department of Forestry and Natural Resources at Purdue University. And welcome, Jake. You're on.
All right. Thank you very much. Can everyone hear me all right? Excellent.
Yeah.
Well, I'm going to share my screen here and get going. So, so I'm an ecosystem scientist. And so what I'm going to be doing tonight is kind of giving you an academic scientist perspective on this. And so there are a few things that come with that are maybe a little bit different than the perspectives that managers and other folks who work on water quality and stormwater issues come from. And I should also say, I think it seems like we'll probably save most of the questions till the end. But if anyone's really confused about something or there's a question that you want to, feel free to jump in and ask. I'm happy to make this more of a discussion than just a top-down lecture. So we're all about, first of all, I'm all about big data and ecological theory, and that's something that's the academic scientists. So we do a lot of projects based around novelty. We're always having to come up with new things. But within that, we try to, particularly if you're me, I feel that it's very important to have research that serves the public good and is and has some applied objectives. Even though a lot of times what you get rewarded for the most as a scientist is that pure science, finding those ecological theories and getting those big papers, but my view is that both of those things can be done together. So policy isn't my expertise. I'm not a manager. I'm not a social scientist or a policymaker, but I like to think about policy because it's important. And if you really want to make your research impactful and meaningful, that's the best way to do it. And so I try and reconcile a lot of different perspectives. Stakeholders can have different needs and different interests, and those aren't always aligned. And that's part of why this is so difficult, is that folks don't always agree on what the best solution is, and the best solution for one person may not really come up with the best solution for other folks. And so then the last thing here, I have advocacy question marks. So maybe you know, maybe you don't, but for the last several decades, I would say, probably even longer, there's been an ongoing debate in science, particularly in ecology, about our role as advocates. The traditional view is that we should be delivering information and we should just say, here's the information, that's it, no interpretation, do with it as you will. But gradually there's been a debate about, well, how much should we be advocates? And I would say that probably the debate's pretty much over, and the advocates have for the most part won, in that it's now pretty open for scientists to talk about how they view these results and to deliver recommendations. And I think it's important to put that out in the open, but also to discuss how I temper that. I think that you can provide recommendations without providing value judgments. So, for example, what I'm discussing today is if you're concerned about stormwater quality and you're concerned about the Chesapeake Bay, and you want to reduce nutrient loads, fix stormwater issues, these are the ways that I think that you should do it. So you can decide whether or not that's your value priority or not. But I think that science can say, well, given those priorities, we think this is the best way forward. And so that's the compromise that I strike. But one thing about scientists is we get in academia is we have a lot of free speech. We can say pretty much whatever we want about research topics. And so that allows us to take that advocate role if we want it. But obviously some folks choose not to, and I think that's a great choice as well. But I think that part of the reason why I accept advocacy is because all of us live in the environment. And so anyone who is studying the environment is also a stakeholder in the environment. We all drink water, and so we all have a stake in having that delicious, clean, fresh drinking water, having places to go out and enjoy the environment, and things like that. But that doesn't mean that we all have the same priorities and the same goals. And so this is a big sweeping picture of that perspective. So across the top here, I'm listing all different kinds of urban streams you find in urbanized or suburban systems. Sometimes you have a stream and there's a protected riparian zone. So it's a stream and there's woods on either side. It's in an urbanized setting, but it's a pre-protected riparian zone. Maybe you have a restored stream. Maybe it's a swale or a bioretention cell. That's a kind of restoration. Maybe it's a buried stream. We see lots of streams that are pipes. Maybe it's a gutter. Maybe it's a wastewater outfall. And so to all of us, these things mean different things. But what I'm highlighting here is that to me as an ecosystem scientist, I think about these as an ecologist all as being streams. To me, a buried stream that's in a pipe isn't really very different ecologically speaking from a normal looking stream with forest around it. And so to me, a gutter is also a stream. If you have a storm event and your gutter's flowing with water, guess what? There's algae in there, there's microbes being transported, they're doing things, they're changing the water quality. And so from an ecosystem scientist, I don't see a lot of difference between a gutter and a stream. In some ways, obviously, aesthetically, they're very different. And also from a policymaker standpoint, they're very different. If you're a manager and you're responsible for regulating waterways, you would never consider a gutter to be a stream from a legal standpoint. And that's okay. You have different priorities. As a manager, you're looking at managing water quality, preventing flooding, improving water quality to Chesapeake Bay, managing total maximum daily loads, things like that. And so we can have both of these definitions side by side, and that's okay. And so that comes to the question. So science and policy, as a result, don't always agree. As an ecologist, I think that a gutter is a stream, but that doesn't mean that policy is ever going to consider a gutter a stream, nor should it. So we have different priorities. Regulations are also written with incomplete and insufficient information. We're constantly learning new things about hydrology, about water quality, about microbes, really learning more than ever. So science is changing very quickly. Science is changing very quickly, but the laws don't change very quickly. And so we're stuck with this situation where we get new scientific information, but we have to fit it into this round holes, the square peg round hole situation. So the Clean Water Act. So I wasn't actually originally going to talk about this, but then last week we had a major Supreme Court decision surrounding the Clean Water Act that has some relevance to this question. So I thought I'd weave that into the story a little bit. So the Clean Water Act is a great example of that. It was the law was enacted decades ago. We have different priorities here. As an ecosystem scientist, I think about where water travels. the Clean Water Act is beholden to the US Constitution, and it gets its power through the Commerce Clause. As you all probably know, the federal government's power is directed entirely through the Constitution. If you can't make a constitutional case for a federal government's action, then it's not constitutional and the federal government can't do it. And so the power of the Clean Water Act is driven through the Commerce Clause. The Clean Water Act is specifically regulating navigable waterways. And so you've got this nice navigable waterway here. That would definitely be regulated with a boat. That would definitely be regulated by the Clean Water Act. And that's because these navigable waterways could be used for interstate commerce. And therefore, through that kind of convoluted reasoning, the Clean Water Act gets its power. And in fact, it doesn't just have power over these navigable waterways, but the power has been interpreted to extend upstream to non-navigable waterways, these small headwater streams, so long as they are in some way connected to these downstream navigable waters. And whether or not they're connected and where that connection happens, where the cutoff for that is, has been now the source of decades, and definitely over the last 15 years, a lot of disagreement. And then there's been a separate issue as well, which is that discharge location matters. So under the Clean Water Act, if you want to discharge a point source, you need a permit for that. But there was a lot of debate over what discharging a point source into a navigable waterway meant. So under the older interpretations that appear to be on their way out now with the Supreme Court ruling, this image on the right. So we have two images here, two landscapes with a wastewater treatment plant, and that's your point source. So it's taking wastewater and treating it, but then it's dumping wastewater effluent that still does require a permit because that is not usually so great water that you can just take a cup and drink it. So it requires a discharge permit. But the question here is whether or not the location matters. And so under a lot of interpretations that have been working up till now, on the right, the wastewater treatment plant on the right is going to require a permit. But on the one on the left, it's not discharging into a navigable waterway or a waterway that's directly upstream of that, what's called waters of the US. And so maybe this one's not going to be requiring a permit. And this is something that's kind of frustrated hydrologists quite a bit because we look at this and we say, well, yeah, that discharge is happening. It's not discharging straight into that stream, but guess what? Everything rolls downhill. And so even if that discharge then is being, so we can have a land application, for example, and you spray this wastewater on the land, and then it seeps into the ground. But eventually that water is going to, and that waste is going to move through groundwater downstream, and it may get treated in the meantime, or you may end up having wastewater popping up in your stream downstream, even though there was no surface connection. But the Clean Water Act was written in such a way at a time when our understanding of science was different. And so it never considered groundwater. And so for a long time, we said, okay, anytime that there's groundwater being transferred, the Clean Water Act has to close its eyes and say, okay, well, that water went underground. And so even if it pops up later, we can't consider it legally. And so once that wastewater goes underground, even if it pops up again later, we can't regulate it. And so that's led to some related issues along with this, have led to this whole debate then of where are the waters of the United States. So as I mentioned, downstream here, you've got this traditional navigable waterway. But as you move upstream, at some point, you're going to say, okay, this isn't part of the waters of the US anymore. And so we've been, for the last 15 years or so, there's been these competing debates about, okay, well, is this wetland up here that's only connected to the river network some of the time? Is that part of the river network? Is that considered waters of the US? A few years ago, probably yes. Now under the new waters of the US rule that was finalized in January, probably not. But we have now this new Supreme Court decision. County of Hawaii versus the Hawaii Wildlife Fund was decided last week. And basically what they said is it doesn't matter where your point source input is anymore. They said that splitting hairs about where the source was, they called it, quote, a loophole. And they said, we don't really care where the source is. We care about what's popping up in the navigable waterway. And so it doesn't really matter if it's going underground, if it's discharged directly into the river, what have you. All that matters is, does the pollution actually show up there? So this then is interesting because it creates this issue where, well, how do we interpret the waters of the US then? If inputs all the way up here then can count if they pop up further downstream. That's, as I said before, I'm not a policy expert, and so I get to punt on that one. But I would imagine we're going to be seeing a lot of court cases now as we try to actually come up with a consensus of how we interpret this new ruling by the Supreme Court. But as the article in Science News said, hydrologists should be happy was the headline, and certainly hydrologists prefer this viewpoint, where we look at the entire system as one whole rather than making these artificial breaks. Obviously, there are a lot of issues there in terms of how much cost is involved with regulating potentially a lot more systems. So that's another concern. And that's another reason why these laws are set up the way that they are. We have to make priorities and judgment calls, and so sometimes protecting everything isn't an option, obviously. But I think that it's good to set your policy with the best science possible. I think that's going to come up with the best outcome for everyone. What this means is that water quality in streams and rivers impacts water quality downstream. And further, because of the way that our legal framework is set up in the United States, a lot of the basis of protection for smaller streams comes from the Clean Water Act and this emphasis on protecting downstream waterways. And that's why we do a lot of work. First of all, we want to protect the Chesapeake Bay. We want to protect the Potomac River and these large waterways. But also a lot of the legal authority to protect smaller streams comes from the motivation for protecting these larger waterways as well. So they're really greatly tied to each other. And so I think that this will be for folks who, so we've got a large range of knowledge levels and expertise on the call. So some of this is probably for those of you working with Chesapeake Bay issues. You're gonna say, I've heard this before. But we have a lot of sources on the urban and suburban landscape for things that cause water quality problems downstream. We have things like wastewater treatment plants, as I've talked about, houses as well. People apply fertilizer to their lawns. People have septic systems in many cases. The sewage systems obviously aren't perfect either. And then we have cars, and cars produce a lot of nutrients as well, both in the form of air pollution and stuff that's deposited on roadways and parking lots and then gets flushed downstream. And so we've identified nutrients like nitrogen and phosphorus as being these fertilizers that when they get down to the Chesapeake Bay, as you may have heard, they cause eutrophication. And so we add too much nutrients from all these urban and suburban sources. There's also a lot of sources that are agricultural as well from farmlands, but we're not talking about those today. But all those nutrients go downstream. They form algal blooms, and then when those algal blooms die, they cause these dead zones. And so here's an image over the Chesapeake Bay of a really severe algal bloom. And then we also have issues with sediment. So submerged aquatic vegetation is impacted a lot by sediment. Research done in the 80s and 90s showed that actually sediment just settles on the submerged aquatic vegetation. in the Chesapeake Bay, and it blocks the sunlight from the leaves. And that's a big source of mortality for SAB. And we've got a lot of sediment, and a lot of this comes in the form of what is known as legacy sediment. And this makes a lot of problems very difficult if you want to deal with sediment, because what happened is that during the colonial era, when we were settling, and then after that, believe it or not, agricultural best management practices weren't all that great. In fact, for tobacco farming, they were actively trying to erode soil from so I'm talking like, this is the topsoil that we always want to protect. During the colonial times, folks like Thomas Jefferson were growing tobacco, and they actually wanted to actively erode that topsoil because they thought that it was making the tobacco taste too strong. And so, we really need to maybe deplete the soils a little bit of all those rich nutrients and organic matter and the things that help plants grow. And so not only did we not have good best management practices, but in some cases we were making things worse on purpose. And then this sediment would collect, particularly behind mill dams, which we had many of. And so you would have this, if you look at stream banks, you've probably seen that a lot of them are incised like this. And a lot of times the sediment that you see that's been cut down is actually sediment from the 17th, 18th, 19th, 18th and 19th century mostly. Certainly 17th century as well. You can see pre-settlement soils all buried underneath all of this very brown, rich topsoil that we very effectively eroded off the landscape in just a couple hundred years. And so here's a little diagram of that. So in the pre-settlement period, we had this nice even topsoil, regular stream banks. And then during the agricultural period, we came in and we downgraded the streams a lot because we had a lot of more flooding events, but we also sent a lot of sediment as well. And so these streams got kind of buried in the landscape a little bit in these incised channels. And so now that we have more urban runoff, all of that sediment that collected around the stream is getting flushed out because urban runoff is accelerating the speed of water and it's increasing the erosion. So all that sediment was sitting there nice and happy for a long time, and now increasingly it's on the move. And so you get images like this that you can see in a lot of different places. And it's because of this urban stream syndrome is what we call it. And that is basically that we see greater impervious surfaces across lands. And so that means that here on the left, we have this forested landscape and rain comes down and most of the water is going to infiltrate into the ground. And here only 10% is going to be surface runoff, so that overland flow. But now on the right here, you've got 75 to 100% impervious surface. This is, a really impacted city, obviously, where almost everything's covered. And there you're not going to have very much infiltration. You get a lot more runoff. And so as you can imagine, if you combine a big source of sediment with a ton of runoff, you've got a lot of sediment moving through your system. Which brings me to, so said this was rethinking the suburban stormwater paradigm. This brings me to my first rethinking hot take, and that is that it's time to accept sediment. So we make a big priority of reducing these sediment loads and doing everything we can to minimize the transport of sediment down to the Chesapeake Bay. I would argue that we have to accept that this sediment is here, and in fact, that some sediment transport is a good thing. So estimates show that sediment will be in these systems in the Chesapeake Bay watershed. Legacy sediments from the Mississippi River in the Mississippi watershed will be in the system for 10,000 or more years. 10,000 is a low estimate. So if we were just let things go as they were, in about 10,000 years, this slug of legacy sediment that we've added to our river networks will eventually work its way out. And then, so let's say that you wanted to have some sort of infrastructure that reduces the sediment load downstream. Well, if you were going to try and do that somewhere in the Piedmont of Virginia, the delay between when you actually started reducing sediment inputs. So you've got this legacy sediment here in this image on the right that's all built up. It's eroding. It takes 100 to 1,000 years for your sediment reduction best management practice in the Piedmont of Virginia for that benefit to be seen all the way downstream in Chesapeake Bay. So this is important, because it's not to say that these actions aren't important. If you need to stabilize a certain area, you have a lot of erosion and you have a local problem, then you may want to deal with your legacy sediments. If it's going to erode and take out someone's house or a road or something like that. But if you're worried about downstream water quality and you want to see a positive result in Chesapeake Bay in your lifetime or in your children's lifetime, then there are probably other things that you can look at. And so this is kind of a graphical representation of why I would argue that these sediments, one of the reasons I'd argue these sediments aren't that big of an issue. And that is that, as I noted, I'm going to back up here for a moment. As I noted here, during the agricultural period, this legacy sediment wasn't that big of a deal. It's only more recently, now that we have these high flows from more impervious cover in our suburban and urban landscapes, we're also getting more high flows from climate change. It's only under this current regime that we're getting active erosion. And so if you reduce the problem upstream, if you decrease that water velocity coming downstream, then maybe you don't actually have to worry about these incised banks. We look and we see an incised bank and we automatically think, oh, this is a problem. But this is me standing in the middle of a very incised bank in the Parkers Creek watershed in Calvert County, Maryland. And this is now part of the American Chestnut Land Trust. It used to be in tobacco farming until the 1950s. But since then, it's been protected and forested. And so this photo was taken in probably 2012. So this system had been reforested for 50 to 60 years when this photo was taken. And you'll notice those incised stream banks are still there. But you'll also notice that they're not bare anymore. They have vegetation growing on them, and they're actually quite stable. They're not really releasing a ton of sediment. And so it may be that actually moving all of this sediment, one argument has been, well, we need to get all of this legacy sediment out of these stream banks so they can stop eroding downstream. Another option is we actually just well, I said just, and that's not, so that solution is not so simple, but I would suggest that we are better served both for sediment and water quality by focusing on reducing stream velocity and then focusing on hotspots and nutrient sources for sediment erosion, but not trying to lock down sediment. Because that's actually, so not only is there a ton of sediment out there, more than we can probably ever hope to manage with billions and billions of dollars, but locking down sediment doesn't necessarily solve the problem. So this is an image here on the left is upstream, and then on the right is downstream of this headwater urbanized stream. So when they developed upstream of this stream, they put in this riprap here. So you can see that this is about 30 feet or so of riprap. And they installed that to control the grade. So they said, we don't want there to be, we think there's gonna be a lot of erosion here on this downslope. And so we're gonna put riprap in so that which is, big boulders, rocks, and that's gonna reduce the erosion. And what it does is that it reduces the erosion locally, but then, and it's a little hard to see in this photo, but the result is that this little stream that's only a few feet wide, downstream of the riprap, it had incised banks that were 3-4 feet high. And you can see above the riprap, there's actually not much incision at all. And so this comes from an interesting fact of physics. And to get to that, I'm gonna take a little bit of a meandering story, but I think that this is pretty cool. And it demonstrates to me why data is important, why just looking at a system, looking at a stream and deciding we know everything about it can be a mistake. So here's a great classic, here's a couple great classic photos of streams. On the left here, we have this rushing, babbling headwater stream. And on the right, you have the Mississippi River, this kind of smooth flowing water. So which one is faster? Up until the 1950s, a lot of even hydrologists would have told you that that rushing headwater stream on the left is moving much faster than the lazy Mississippi River. Well, along came someone named Luna Leopold. And if your name Leopold's familiar to you, maybe because his father, Aldo Leopold, wrote a Sand County Almanac. Well, Luna Leopold was pretty cool too. He ended up being the chief hydrologist of the United States Geological Survey. It's a picture of him. He traveled all across the country surveying the hydrology of rivers and streams and having what seems like generally a pretty cool job. And he said, well, let's take a look at some data here. So because rivers tend to be steep, this is from his paper in 1953, because rivers tend to be steep in their headwaters and flow at flat gradients near their mouths, it appears logical to suppose that the velocities are great in the headwaters and decrease downstream. But he took data from more than 6,000 gauging stations that the United States Geological Survey maintains. And we maintain a lot of this network to this day. And he said, wait a minute. So on the x-axis here, so as you move left, right, that's discharge. So that's the amount of water that the river is moving. And so bigger rivers are on the right. And on this y-axis here, up and down, that's mean velocity of the river. And so what you can see is that actually, and this is a national data set, and you could add another couple thousand points and you would get the same relationship. And what this is saying is that, in fact, as a river gets bigger, the velocity always increases. Not just usually, it is as close as you can get to a law in river hydrology and geomorphology. Velocity is always increasing downstream. And so we can look at these pictures and we can make these judgments. We hear a loud babbling brook. We see the silently, smoothly moving Mississippi, and we've made an assumption. But in fact, when we take data and look at it, we realize that the situation is the opposite. And 1953, that's not that long ago to be completely wrong about the hydrology of every river and stream. So there's a lot of things that we don't know. And so here's another one. So we've got, so here's a question. Which stream is flowing water more? On the left, we have a geomorphic natural channel design, stream restoration. And these are based off of restoring channel meanders, adding rock veins and things like this. And the idea is that these baffles will slow down the travel of water. And so, as I mentioned before, a big objective here is we want to reduce the water velocities. This water's coming fast off of urban and suburban landscapes. And so we really want to slow that water down. Well, so this is a way to do that. We restore some of the natural attributes of the stream channel. We add in things like these rock veins, and they're going to slow down the water by buffeting it. And then on the right here, we have the alternative, which is a stream that is chocolate soup. It's picking up a ton of sediment and it's moving it downstream. Which stream is slowing down water more? Well, this is just to get a little bit nerdy here. Stream flow is reduced primarily by work in river networks. And I'm saying work here in the physics sense. And so what work means is that you're moving something from point A to point B in the classic Newtonian sense. So here's hot take number 2. Moving sediment does work, not baffles. And so in fact, these baffles can't be expected to reduce stream flows a whole lot. And so we see these systems fail a lot. And it's because they can't slow down water. But in fact, sediment being transported, the very thing that we are often trying to limit, is the very thing that's also going to slow down water. And so we have this conflict here where if water velocity is fast, pretty much the only way that you're going to slow it down is by moving sediment. And so streams are doing a lot of work. When they're really moving, and you see that chocolate soup, they are transporting a lot of sediment. A lot of that, some of that sediment is actually entrained, floating along in the water column, but a lot of it is what we call bed load. It's just particles that are skipping and bouncing. It's called saltation along the stream bed. But that's every time the water picks up that particle, carries it a bit and drops it down, it's doing work. And by doing so, it's reducing its energy. So moving sediment does work, but when water hits a baffle, so you see this fast flowing water is hitting this rock, it's splashing up, it's making some noise, it's creating white water. This is a collision that's actually largely elastic in the physics sense. Water's hitting that rock, and when that happens, energy is released. That energy is released mostly in the form of heat and sound. If you have a really strong collision, if you smash two rocks together, you can get those sparks forming. That's heat being dissipated, or energy being dissipated in the form of light in that case. And so that's what, when water hits a rock, heat, light, and sound are the ways that energy is dissipated. And yeah, when you hear a stream flowing fast, you hear the rushing water. That's actually not dissipating very much energy. You're dissipating way more energy actually moving sediment. And so this is an issue because, so this is two cross sections here. This is on the top here, this is that picture I showed you, drawn as a diagram. So this is your stream profile. And they said, okay, well, we're worried about erosion. And so we're gonna put in this riprap here along this reach. And so, yeah, that's gonna, the small arrows here, because it's saying, yeah, erosion is not very large across that reach, but you actually haven't dissipated all that much energy. And so when you get below that reach, your erosive power is actually doubled. And so that's why you'll see this, this sediment being scoured out, and you get these incised channels directly below riprap or any sort of system that's trying to stabilize and hold sediment there. And in fact, a great example of this, and I'm kind of hitting my forehead now, I should have put some pictures up of this. If you go downstream of a dam, you will see this very clearly. Dams hold all of the sediment. They release water, often at a very high velocity, and it's carrying very little sediment. And so it's not depositing any new sediment below the dam, but it's scouring out that dam. And so below a lot of dams, you see these rocky canyons, all the sediment's been scoured out. Well, we get the same thing if we try and armor one reach of a stream, but not armor the downstream reach. We get all of that power just gets moved downstream. And so in this bottom scenario, this is without the riprap. Yeah, you still have erosion, but it's evenly spread throughout this entire reach. So the alternative then is you want to slow down water before it gets to the stream. Increasing infiltration is a great way to do this. We talk about swales. These are bioretention cells, which is often a fancy name for a swale, but they're headwater structures. Stormwater ponds are another example of that. There are a variety of systems, and there are increasingly stream restoration strategies that are trying to take this approach into account. But the problem is that having water infiltrate to slow it down, having these sorts of advanced strategies, they take up a lot of space compared to a stream restoration, and they can be very expensive. Stream restorations are expensive, but bioretention cells are probably even more expensive when you look at the square footage. So it's not a, you know, this is where that original preamble about me being an academic comes into play. I'm talking about here in just perfect scenario, we would reserve space, we'd reserve money, etc., to protect these systems. Well, a lot of times we don't have the space to put in a bioretention cell. We don't have the money to do this everywhere. So what's the compromise? It's a tough problem, but my argument is that we really need to lean more into big data and really iterative design strategies. Every single management strategy, restoration design, every single ecological model, they all have flaws. But if we take a data-centric approach and really try to dig into these questions and say, okay, where is a certain strategy optimized? What are some scientific data-driven tools that I can use to optimize that strategy? That has a lot of benefit. So that's my teaser for next time. And so next time, in addition to talking about how I think that we can work together, more ecologists, engineers, managers, to make better suburban stormwater management strategies and restoration designs, but I'm also going to deliver some more hot takes. For example, did you know that we don't have enough data to estimate the water quality impact of stormwater ponds? We give them nutrient credits for retaining nutrients, but these are very rough estimates. And so that's not something where anyone is particularly to blame. It's very expensive to collect more data, but I'm going to talk next time arguing why I think that the data are worth it. And it's because we discover exciting things, and sometimes we find good news. So I'll be talking next week also about how climate change may actually improve water storage. We've been really worried that climate change is going to increase runoff with more big storms, more hurricanes. Well, some data coming in suggests that may not be the case. So sometimes data shows us that the pessimistic outlook is not really the case, and that's important because we need to know how to spend our money. If we're going to really solve these problems, every penny counts, and the best way to optimize these solutions is to figure out where the best bang for your buck is. So that's it for today. I hope that you all found that to be interesting, and hopefully we can have an interesting discussion as well.